Welcome to the Statistical Power page of Research Engineer. There are 5 specific empirical components that affect statistical power in applied research. The first one is the scale of measurement of your outcome, be it categorical, ordinal, or continuous. Your research design, be it between subjects, within subjects, or multivariate. The magnitude of your effect size, being small or large. The variance of your effect size being limited or extensive, and your sample size being small or large. Click on any of these text links to learn more about the effects of each of these on statistical power, or click on the Statistical Power button to start the Statistical Power decision engine that will work you through each phase of these 5 empirical components. As you scroll down, you'll come to statistical power and isomorphism. In my statistical consultation practice, many people come to me and say, Eric, how many people do I need to find a significant p-value, or how many people do I have to collect to have significance? This is an extremely important part of planning any study, and an a priori power analysis or sample size calculation gives you an idea of how many observations of the outcome will be needed to detect a clinically meaningful effect or the effect size that you're interested in. One framework that I used to gain an understanding of statistical power was isomorphism. Isomorphism is the systematic interdependency between empirical constructs. A change or decision made in one of these 5 areas will cause a predictable, logical, and static change in other associated constructs. Here are some fundamental principles that explain how isomorphism works between these 5 components. When using a categorical outcome, you'll have decreased statistical power and increased sample size due to limited precision and accuracy in categorical outcomes. The same holds true for ordinal outcomes. They'll decrease statistical power and increase your needed sample size. However, with continuous level measurement, you have increased precision and accuracy, which increases your statistical power and decreases your sample size. Moving on to research designs, a between subjects design will decrease statistical power and increase sample size because you have to collect more observations to have independent groups that are comparable. Within subjects designs will increase statistical power and decrease your sample size because each participant serves as their own control. With multivariate designs, you'll decrease statistical power and increase your sample size, and this is due solely to the fact that you need more observations to understand the multivariate associations and confounding effects of variables on each other when predicting for an outcome. If you hypothesize a large effect size in a relative sense, this will increase your statistical power and decrease your sample size. This is because larger effect sizes are easier to detect. Smaller effect sizes that may be clinically significant lead to less statistical power and an increased sample size. You'll need many more observations of the outcome to detect the nuances of variance when you have a small effect size you're trying to detect. Limited variance or homogeneity in a population will lead to more statistical power and decrease your sample size. Extensive variance in the outcome or heterogeneity will decrease statistical power and increase the needed sample size. Finally, every time that you have a large sample size, you'll increase your statistical power and you'll be able to detect both large and small effect sizes regardless if they have limited or extensive variance. And with small sample sizes, you have a decrease in statistical power and a decrease in flexibility of effect sizes. You won't be able to detect small effect sizes or effect sizes that are very heterogeneous with a small sample size. Therefore, there's a decrease of statistical power. Click on the statistical power button to continue.